So we're going to begin with 3.5, the undetermined coefficients or non-homogeneous problems. So this is a jump in terms of difficulty from 3.1 to 3.4. But the thing about this type of problem is you're still going to have to do the homogeneous component of solving a differential equation. So what you learned in 3.1 to 3.4 is still going to be very useful, in fact, necessary to be able to do any of these problems, right? So we learned how to solve ay double prime plus by prime plus cy equals 0. Now we want to be able to solve when it's not equal to 0, essentially, right? And we'll use g of x. So the idea behind this method, and this is what makes it most difficult, is it's not a like, oh, this is a formula, you just get the answer. It's more of like we kind of have to use a little bit of reasoning and an educated guess to find the answer, right? And that's what makes it the most difficult. So the method of undetermined coefficients. Now, there are more than one method, but this is by far the easiest, in my opinion, of all of them. Um, we'll use educated guesses for what the solution will be. The other methods require integration, and this one does not. So educated guesses for the potential solution. So at the end of this, I'll give you a table, and basically, if it looks like this, it's this. If it's like this, it looks like this, right? So that's going to be the idea. But before we get there, let's remind ourselves what the non-homogeneous differential equation is. So a non-homogeneous differential equation is one that does not equal 0. So just a generic example. Now we're going to start solving like this. So you kind of have to think about it this way. What is a solution to a differential equation? It's a function that makes the left side equal to the right side, right? So if I can think of a number that will make the left side be equal to 27, that's what I'm aiming for, right? So any function free of arbitrary parameters. What that means is there's no C1, C2. Um, in your differential equation that satisfies the differential equation is called a particular solution. And we denote it as YP. Denoted as YP. The solution to any non-homogeneous differential equation, so NH will stand for non-homogeneous, um, is going to be y equal to the homogeneous solution plus the particular solution, which we often abbreviate as YC and YP. So another name for the homogeneous solution is the complementary solution, where YC is also called the complementary solution. So no matter what you're doing, you're always going to have two answers or two parts to the answer. Your homogeneous part and your particular part. Now, there will be some questions where I only focus on the particular solution. So one of the things that I highly recommend when you do these problems is to read the directions because you don't want to do more work than you need to. Okay. Sometimes you only need to do the particular, but there are cases where you have to do the homogeneous anyways, because you want to make sure there's no repeated roots to deal with, which we'll talk about later. So let us begin by solving a non-homogeneous problem and kind of build some tools that we want to think about when we're doing this, right? So, example, solve the differential equation y double prime minus 4y equal to 3e to the 3t. So I want you to think about this in the most uh, general way. What I'm asking you for is a function that makes the left side equal to the right side, right? And if you plug in a number, let's say zero, like what if you plug in zero? Well, if I plug in zero, zero minus zero is zero, but then e to the zero is one, so does zero equal three? No, so zero doesn't work anymore. That's why that non-homogeneous part comes in, right? So I need an answer that when I plug in to y double prime and y, that it's going to be equal to 3e to the 3t, right? Like it has to do that. So in order to find the solution, though, I got to find the homogeneous part because, and this will make sense in a little bit. So step one, formula. Sorry, find YC. Actually, no, let's do formula. No, we'll do formula here. Formula. Y is equal to YC plus YP. That's all you got to write down. Just to remind you that there's two parts to the answer. Complementary, particular. Step two, find YC. So now we're just doing 3.1, 3.2, 3.3, 3.4 here. R squared minus, now it's 4y, not 4y prime. That's very important. So R squared minus 4 equals 0, right? Set equal to 0. Because it's the homogeneous part. So you're not doing anything with the 3e to the 3t yet. So then r squared is equal to 4, and then r is equal to plus or minus 2. So that means the complementary solution is C1e to the negative 2t plus C2e to the 2t. So I have the first component of the solution. That's great. Now, for step 3, this is where we start to get into the particular part of it, is we're going to make that educated guess, right? So pick an educated, sorry, that's not a proper way of saying it. Pick a function that could work. I want you to think about this logically. If I want the right side to be 3e to the 3t, sorry, the left side to be 3e to the 3t, so it's equal to, right? This is my end goal. 3e to the 3t equals 3e to the 3t, right? Like that's what I want. What function will accomplish that? Well, it's not going to be sine or cosine. It's not going to be x squared. It has to be e to the 3t. So my particular solution is going to be equal to e to the 3t. But I don't know what number is going to be in front of it because I have this double prime. I have derivatives. I have other numbers to deal with. So in an ideal world, a would just be 3 and I'd be done, right? But I don't know. So I have to put a coefficient. That's where that undetermined coefficient name comes into play. You don't know what it is. But structurally speaking, I know that the right side's e to the 3t, so my particular solution should have e to the 3t, like it has to. Otherwise, it would be impossible for them to match up. So it's that. That's our guess. If you're wrong, you're wrong, but that's our guess for right now. Step 4 is find derivatives. because you're going to plug them into the differential equation. So find derivatives. So yp is equal to ae to the 3t. Y prime of p is equal to 3a e to the 3t. And then y double prime p equals 3a times 3, so that's 9 e to the 3t. Just like that. So now I have the tools to plug this into my differential equation and see what happens, right? So that's my next step, step 5. Sub in yp into differential equation. So y double prime minus 4y equals 3e to the 3t. And so we end up getting is 9a e to the 3t minus 4 ae to the 3t equals 3e to the 3t. Just like that. And so my goal is to find a value of a that makes both sides true. So we'll do some simplification, right? So 9a, all right, sorry, let's make that step 6. Simplify. 9a e to the 3t minus 4a e to the 3t equals 3e to the 3t. And so I get 5a e to the 3t equals 3e to the 3t. If I want both sides to be the same thing, I just need to make them look exactly the same, right? So what's the value of a going to be? Well, I can divide out e to the 3t. And so 5a is equal to 3. A is equal to 3/5. So I have found a solution that makes both sides equal to each other, the particular solution, right? So then step 7 is your final solution. So plug into formula. Y equals YC plus YP. So then Y is equal to C1 e to the negative 2t plus C2 e to the 2t plus 3/5 e to the 3t. And that is our non-homogeneous solution. Now, if you're wondering, how is this the solution? Because I'm thinking in my head, well, if I want the left side to be equal to the right side, how does that e to the negative 2t and e to the 2t, how do they not like get in the way of getting to like both sides being equal to each other? Well, here's kind of like the magical part. And this is like so subtle that if you don't understand, it's perfectly understandable because it's kind of subtle. Remember, when you're solving the homogeneous component, YC, what is your equation equal to? It's equal to 0. So what does your solution trying to do? Your solution is trying to be 0. So the reality is this whole thing right here, this is actually equal to 0. Like the way you combine them together, in the end, just cancels each other out, and you're left with only YP. But you need it there to get the full picture, right? So it may not make sense right now why we need that component, but that component is necessary because it gives you the entire picture of what the function is doing. In the long run, the true behavior of the differential equation becomes the particular solution. But in order to realize that, you kind of have to have everything. And the best example will come up in section 3.8, where you're doing impulse functions with mass spring systems, where the particular solution is how the solution behaves in the long run, but the initial part of the solution is affected by the homogeneous part. So your response to a system could be like this, and then it levels out and it does that forever, right? This right here is the particular part. That's what creates that steady state. But the initial part is influenced by the homogeneous part. So combining them all together creates this specific type of response, right? So that's how we need it. But in the actual grand scheme of the solution, the homogeneous part is just 0. It's just a fancy 0. That's all it is. So now we're going to look at an example with polynomials. And the thing that gets very annoying about a lot of these, honestly, is the fact that the algebra becomes very, very intensive, where there's a lot of room for error just because of signs, foiling, distribution, combining like terms. So the differential equations part, very easy. It's the algebra that kind of kills you in these types of problems. So just got to be very, very diligent in when you're writing things down. So solve the differential equation y double prime plus 4y prime minus 2y equal to 2x squared minus 3x plus 6. Now, first example, exponential. So there's really going to be like three styles: exponentials, sine and cosine, and polynomials. Okay. And then we can start combining some of them together. But those are the basic three: exponentials, polynomials, and sine and cosine. So for this one, step one, formula. So y equals yc plus yp. Gotta remember, homogeneous, non-homogeneous. Step two, solve for yc. Notice that step two used to be four steps in 3.4. Now it's just one step in 3.5, right? Because it's the whole process is kind of condensed down to one part of this. So r squared plus 4r minus 2 equals 0. Remember, you're setting it equal to 0. There's not a homogeneous, sorry, non-homogeneous component to it. And then if we can factor it, great. If we can't, then we can't. So I believe with this one, we can not factor it. So we'll do the quadratic formula. So this is going to be equal to negative 4 plus or minus the square root. 4 squared minus 4 times 1 times negative 2 all over 2 times 1. So then r is equal to negative 4 plus or minus 16 plus 8 over 2. So r is equal to negative 4 plus or minus the square root of 24 over 2. Here's the thing, this isn't really going to make a difference to the answer. So the complementary part being ugly for at least this example doesn't make a difference, right? So then r is going to be equal to, I don't know, 24, 2 and 12, 2 and 6, 2 and 3, so 2 radical 6. So negative 2 plus or minus rad 6. Don't worry about that algebra. That's just the answer. So there we go. Which means yc is equal to c1e to the negative 2 plus square root 6t plus c2e to the negative 2 minus square root 6t. You wouldn't get like something like this probably on the exam. But again, the real part that I want you to focus on in this entire chapter really is the non-homogeneous part. But I mean, this is like the ugly answer. Oh, the way I wrote it down is not incorrect per se, but the homework would mark this wrong. Make sure you put parentheses around the entire number because your computer, the software, will only multiply the square root by t if you don't put parentheses around it. So that's a very easy mistake you can make if it's like not reading it correctly. All right, step three, pick a YP. So again, we use the logic of I want YP to look like what the right side is. Well, the right side is a quadratic, x squared plus x plus 1-ish, right? So my best guess is that it's going to be ax squared plus bx plus c. Okay? That's just the structure that I'm going to be using. So then I take my derivatives. So the derivative of yp is equal to ax squared plus bx plus c. Y prime of p is 2ax plus b. And then y double prime p is just 2a. So we have our derivatives. From there, I am going to plug it into my differential equation. So that's my next step. Make sure it's step 5, yep. Plug yp into differential equation. So y double prime plus 4y prime minus 2y equals 2x squared minus 3x plus 6, right? So we are going to plug in what we know, and that's going to be 2a for y double prime plus 4, and it's going to be 2ax plus b minus 2, and it's going to be ax squared plus bx plus c equal to 2x squared minus 3x plus 6, like that. And so that's our. So now comes into the idea behind what we're doing here. So again, what is our goal? Our goal is to make the left side equal to the right side. So our right side has an x squared, an x, and a number, which means on the left side, I need an x squared, an x, and a number. So that's how I'm going to group it all up. I'm going to group all the x squareds together, all of the x terms together, and all of the numbers together, right? So step 6 is to group by x squared, x, and constant. So we're going to FOIL 2a plus 8ax plus 4b minus 2ax squared minus 2bx minus 2c. Making sure I didn't miss one. Yep. Equal to 2x squared minus 3x plus 6. And so if we group everything up by the correct variable, and we'll even use a little bit of color here, all of the x squared terms are right here. All of the x terms are right here. And then all of the numbers are going to be right here, and right here. And so we get negative 2ax squared plus 8ax minus 2bx plus 2a plus 4b minus 2c equals 2x squared minus 3x plus 6. Right? Like, that's all I've done. And because you can factor out things that share common numbers or variable, that's what we're going to do. So you don't have to do it for like the first one, but to make it obvious, we're going to do that. And then for the constants, you can just put a box around them essentially. And there you go. We have accomplished our goal of combining them together. Now, if you're wondering, why am I doing this? Well, that's the key thing you kind of have to understand is like the why, because the why here is extremely important and it makes this whole process make actual sense in what you're doing. Okay. So I'm going to give you a motivating example on the next slide. Okay, so it's going to be a side note. So motivation for process. Okay. You don't overthink this if you're like watching this right now, if you're listening right now. I don't want you to overthink this because the answer is exactly what you think it is. So don't overthink it. If my goal is for the right side to be equal to the left side, what should the numbers be that are missing? Well, if I have x squared on the left side and I have 7x squared on the right side, well, the number that would make them equal to is 7 and 3 and 5, right? Because those numbers are just missing. So that's what makes them equal to each other. Hopefully that makes sense. Now I am doing the same thing, but instead of it being one number or one unknown variable, rather I am just making it a little bit more complicated. This is what I'm doing now. I'm saying, okay, same idea. Okay, same idea. But instead of it being just a number that I'm missing, what if I wrote down here a plus b? And I wrote b plus c. And right here, I wrote, let's say c, right? Then you would say, okay, if I want the left side to be equal to the right side, well, I want this to be equal to that. What does the left side have to become? What number does it have to be equal to? It has to be equal to 7, which means what? A plus B has to be equal to 7. This means right here, B plus C has to be equal to 3, and then C has to be equal to 5. That's all I'm claiming here. Right there and right there. And that's the magic of it. And if you feel comfortable with that logic, then you can do all of these. It's just that's the big step that you kind of have to make here, is understanding why we're doing it. It's just because I want the left side to be equal to the right side. And then from there, right, C equals 5, which then means B, oops, sorry, b plus 5 equals 3, so b is equal to negative 2. And then you plug that into here, and a minus 2 equals 7, a equals 9. So I found all three of my values using a process of back substitution. If you feel comfortable with linear algebra, you can do systems of equations here, but it's kind of up to you and the method you prefer. So that's the whole process, right? So now we're going to set up a set of equations to solve. So using that logic, step 7 is to set up equations. Let's do it after this. So step 7, set up equations. Now, I know it sounds like, wow, there's like 10 steps here. It's because I'm just expressing every little detail. You can condense down into as many steps make sense to you. So set up equations for coefficients. And just so that we can have it right in front of us, that way we know what we're talking about. Bring it over like that. And so the way I set it up personally, and a bit to be, when I first learned this, no one explained to me like what was going on. They just said like set up this table of equations and solve. Like no one explained this part to me. Like I kind of had to, from teaching, I kind of figured this out. So, trying to save you that hassle of like, well, where does this table come from? It doesn't make sense, right? Because when I learned it, no one explained this part to me. So basically, I'm just creating an equation for x squared, x, and my constant. I'll just use c for constant here. So left side, right side, negative 2a equals 2. Left side, right side, 8a minus 2b is equal to negative 3. And then all of this equals 6. 2a plus 4b minus 2c equals 6, right? Left equals right. That's what I'm kind of doing here. And from here, you just solve for a, b, and c. So if I want to solve for a, b, c, what I would do here is I would start with the easiest equation. So negative 2a equals 2. So a is equal to 1, negative. Then I go to the next equation, right? 8a minus 2b equals negative 3. So 8 times negative 1 minus 2b equals negative 3. So negative 2b is equal to negative 11. right? Because I added it over, but that's not true. It would be added over, so that'd be a negative 5, right? And then, nope, positive 5. Take it back. And then b is equal to 5 halves negative, like that. And of course, now that we have a fraction, our life becomes more annoying. So 2a plus 4b minus 2c equals 6. 2 times negative 1 plus 4 times negative 5 over 2. Well, not too bad because those kind of become nice numbers. Negative 10. If I add over 12, I get negative 2c equals 18. And so c is equal to negative 9. And that's my coefficients. So then my final step is the solution, right? Step 9 is solution. Y equals YC plus YP. So that's going to be C1 e to the negative 2 plus square root of 6t plus C2 e to the negative 2 minus square root 6t plus negative x squared, I guess, so minus x squared, minus 2, sorry, 5 halves x minus 9. And so that's our answer. Is it pretty? No. But is it correct? Hopefully. So now we're going to investigate dealing with sine and cosine, right? Solve the differential equation y double prime plus, nope, minus y prime plus y equals 2 sine 3t. So step 1, formula. Step 2, solve for yc. That equal to 0. So r squared minus r plus 1 equals 0. We're going to have to use the quadratic formula because it's complex. Now, if you're wondering, how do I know it's complex? Well, actually, you don't. But usually if sine and cosine are on the right side, the left side tends to be sine or cosine. They usually match up, but it doesn't have to be. But either case, I look at it and I realize I can't even factor it, so not anything shocking. And we just plug everything in. And so we get 1 plus or minus the square root of 1 minus 4, so negative 3 all over 2. And so we get 1 half plus or minus I square root 3, right? It's not uncommon, oops, I forgot the 2, to have radicals specifically with sine and cosine because they kind of happen from time to time. So not the end of the world with sine and cosine. So YC is equal to E to the 1 half t, because that's alpha, right? That's our solution, times C1 cosine square root 3t plus C2 sine square root 3t. Right, this is alpha, and this is beta. Oops, I forgot the 2 right here. It's there. Can't forget about that. And we have our particular solution. Now, here's an interesting thing about sine and cosine. If you pick only sine or only cosine in many problems, you will run into a situation where it's unsolvable, right? And so just to show you that example here, okay, we're going to pick yp is equal to, and just kind of following the same behavior, we're going to say yp is equal to a sine of 3t. If you're wondering, do I need to match the number inside of the sign like that 3t? The answer is yes, they do need to match up, because if they don't, then you can't really do any of the algebra. So yes. Okay. And so if we take our derivatives, right? So step four is derivatives. I'm warning you ahead of time if you've already done this before. This is going to end up being incorrect, and we're going to have to go back and change all of this. But I want to show you what happens when you don't pick the correct particular solution. So yp is equal to a sine 3t. Remember, chain rule here is very important. It's going to be 3a cosine 3t. Remember, sine comes cosine. Cosine becomes negative sine. Negative sine is negative cosine, and the negative cosine cycles back to sine. So it does cycle. Remember that because it's very important. And then y double prime p is equal to 9 negative a sine 3t, like that. So there will be negatives that you have to deal with. Please be careful with that. Okay, step five, plug into differential equation. So y double prime minus y prime plus, just make sure I get the right number, y equals 2 sine 3t. I just want to make sure I don't forget a 3 in any of those. And if I plug them in, I get negative 9a sine 3t minus 3a cosine 3t plus a sine 3t. So we have our equations. Then we combine like terms, right? So we're going to simplify. I want to make sure what step did I call that? Group. Yeah, sorry. Group by terms. So group by sine and cosine. So negative 9a sine 3t plus a sine 3t minus 3a cosine 3t equals 2 sine 3t. And then negative 9a, sorry, and a sine 3t just become negative 8a sine 3t minus 3a cosine 3t. Now, if you're wondering, hold up, I don't have a cosine anywhere. So what am I going to do with that 3a? Well, if you don't have a cosine on the right side, I mean, you could actually just make one up. And what I mean by that is there's a special number that when you multiply it, it goes away. So theoretically, if you wanted to, you don't have to, but know that there technically is a cosine 3t times 0, right? That's there. You don't have to write that down, but it exists. Okay. So if you're ever missing a term, right? So missing term, it just equals 0. It just set it equal to 0. So then I set my equation. So step seven, right? Let me just make sure, is set up equations. So we get negative 8a and 2. And we get negative 3a and 0. So for sine, we get negative 8a equals 2. And then for cosine of 3t, we get negative 3a equals 0. So here we're saying a is equal to negative 1/4, and here we're saying a is equal to 0. So we're saying a is equal to two numbers at the same time, which is a contradiction. We can't have a be two numbers at the same time that satisfy two equations. There's no way to satisfy both of these. So that's the problem, is we can't solve for a because a isn't unique here. So what does that mean? It means we didn't pick a good particular solution. So this was bad. So how do I correct for that? Well, if you think about it logically, my other option, I guess I could have tried cosine, but if you do cosine, you run into the same issue. It's just you can't solve for everything. So then you know from experience that in this chapter that the complementary solution was always sine plus cosine. So why not try that? Why not try using both sine and cosine? Like that seems like the most safe thing to do. So that's what we end up doing is we're going to go back and we're going to add cosine to it, right? So it doesn't really change much beyond now we just have an extra function to deal with, so it's going to be more algebra. It's going to be a little bit more annoying, but from the overall perspective, it's the same thing. So if you felt comfortable doing it with just sine, cosine's the same thing. It's just a lot more derivatives now. So derivative of the cosine is the negative sine, so minus 3b cosine. Nope, that should be a sine. They should always be opposite of each other. So, and what I mean by that is you should never have like cosine plus cosine or sine plus sine. They should always be one and the other. And then the derivative of sine is the cosine, so negative 9. There is a lot of patterns to this, so you might catch up on some patterns like how the sines always behave a certain way. It's normal, right? The annoying thing about this though is plugging it into your differential equation gets really huge. Like I will not have enough space in one line to fit it all in, which is kind of annoying sometimes. So you just kind of have to squeeze it all in and write it in multiple lines. So we're going to erase this. And what it ends up becoming is, oops, wrong one. Negative 9a sine 3t minus 9b cosine 3t. So that's y double prime. And then minus, right? And when we end up getting is the 3 and negative 3b. So 3a cosine 3t minus 3b sine 3t. And then we just get our original one. So plus a sine 3t plus b cosine 3t is equal to 2 sine 3t. So as you can see, that's a lot of writing, which makes this the most annoying thing. And yes, we are going to group them up by sine and cosine still, so that part does not change either. So just combining everything and moving things around, we're going to get negative 9a sine 3t plus 3b sine 3t minus, no, plus, correction, a sine 3t. So that's all the sine terms. And then plus all the cosine terms. So negative 9b cosine 3t minus 3a cosine 3t plus a, nope, it's a b, cosine 3t equal to 2 sine 3t. Poor 2 sine 3t, just gonna never fit in. And then we can combine like terms and then basically reduce this down to an equation that we can solve. So we get negative 8a plus 3b, and then we get sine 3t plus, and then in parentheses, we get negative 9b, oh, negative 8b. Now, if you're wondering, wait, I'm kind of noticing that the numbers are very similar, just maybe opposite signs. Like notice that we have negative 8a plus 3b and negative 8b minus 3a. Is that something that happens? Yes, it does actually happen a lot. It's part of the pattern to it, actually. Um, so not random, but in the end, it's just kind of cool. And now we set up our equations, just like that whole process that I mentioned earlier. We want the left side to be equal to the right side. Now we have a sine and a cosine that we can deal with. Now remember, it's not there, but just for the sake of seeing it, we do have a 0 cosine 3t just to make sure, like, hey, that's what we're doing. And so we're going to set up our equations. And so our equations end up being negative 8a plus 3b equal to 2. And then we get negative 8b minus 3a is equal to 0. And it's at this point that you can use whatever technique you want to use to be able to solve this type of system. Here, I personally would use linear algebra because to me, I'm just more comfortable with it. But if you're not comfortable with linear algebra, I would probably use substitution here. It's against a personal preference. Or elimination method. The only thing with elimination method is none of the numbers work out nicely enough. They're all kind of annoying. So it's kind of a personal preference, but I will do substitution. So let's go to the next slide. So step 8, solve for a and b. So we got negative 8a plus 3b equals 2. And then negative 8b minus 3a equals 0. So I'm going to solve for, doesn't matter which letter you pick, I'm gonna solve for b. So negative 8b minus 3a is equal to 0. Negative 8b equals 3a. B is equal to 3/8 negative a, right? That makes sense. As long as I pick the right equation. Oh yeah, I'm just looking at. Yep. And from there, we sub it in. Actually, just so I can have plenty of space here. And then sub into other equation. Actually, I'll do it up here. B equals negative 3/8 a into other equation. So negative 8a minus 3b equals 2. Negative 8a minus 3 times negative 3/8 a equals 2. And you'll often get fractional answers here, like there's no avoiding it. 8a equals, not 8a, plus 9 over 8a equals 2. And then combining fractions and all that stuff. So we need a common denominator. So we want 8. So that's going to be negative 64 over 8. A plus 9 over 8a equals 2. And then 9 minus 64 is going to be a 55. 8a equals 2. If I multiply the 8 over, I get negative 55a equals 16. So a is equal to 16 over negative 55, which doesn't make sense to me in my brain. I think I made an algebraic mistake here. So let me just look through here. I think I made a sign error. Yep, it should be plus 3b. That's the incorrect part. And so that makes this whole thing minus. That makes more sense. There we go. Because I was supposed to get 73, which I now get right here. So 73 and 73. See, sign errors, they'll always get you when you're doing these problems. So that's why you got to pay attention. And me showing these mistakes in the video is just to show you that it happens even at the most random times. So always be on guard for sign errors, right? So we got A. Yay. Now the nice thing is I already have a relationship for B, right? So I can solve for B now using B equals negative 3/8 A. B is equal to negative 3/8 times, was it negative 16 over 73? To multiply, you just multiply straight across, right? Positive 54. That sounds about right. Nope. 6 times 3 is 18, so 48. That's the better answer. And then 73 times 8 is probably some kind of large number, like 600 and something. Although, you could do like cross cancellation. I'm sure some people are thinking like, well, couldn't I just do cross cancellation? Absolutely. And then you got to simplify this. So how would I simplify this? I just divide by 2 until I can't anymore. So divide by 2, divide by 2. So 584 divided by 2 is 292. And then I divide by 2 again. And then I get 100 and something. Not very great with mental math right now. 146. And then could I think of bigger numbers to divide? Absolutely. I am just going to choose the easiest path for me. So 73. And there it is, because 73, I think it's a prime number, but I know 6 and 73 aren't going to have any common divisors. So there we go. I got B. All that work. Step 9, solution. So now we just combine it all into one solution. So y equals yc plus yp, which then means y is equal to c1 cosine. Except I think I forgot the exponential. I did. E to the negative 1/2 t, c1 cosine of square root 3 over 2 t plus c2 sine square root 3 over 2 t plus, and then now I got to do cosine. Make sure you put the correct coefficient with the correct sine or cosine, because I've seen people do it all correctly and then they put a with the wrong thing. So a was relegated to sine, b was cosine, it looks like. Yep. So a is going to be negative 16 over 73 sine 3t plus 6 over 73, except I'm out of room. Now, if you're wondering, I noticed the particular solution had 3 and the complementary had square root 3 over 2. Are they ever potentially going to be the same number, like they all have 3? And the answer is yes, that is a possibility. But the reality is, if you get a problem like that, it's going to be way worse because then you're going to have to deal with repeated roots, essentially, um, or sorry, not repeated roots, linear dependence. You do not want a problem where all of them are sine or cosine 3t because you've made the problem going from hard to almost, it's not impossible, but it's like way harder than you would want it to be because now the hard part is the derivatives. You got to take a bunch of product rules and these functions get massive and then you got to combine them all. It just becomes a algebraic nightmare more than anything. So on an exam, we would not give you one of these where they're all the same because it would take you 2 hours just to do that one problem correctly and, with more than one try, right? So you don't have to worry about that. With the exponential, we can kind of get away with it because they're way faster because exponential derivatives are very simple. But with sine and cosine, it would be too much of a computational nightmare to do that. But yeah, that's how you do it. If you're wondering, C1 and C2, what is that process like? Well, I would give you initial conditions and now you solve for it. You can't solve for the initial conditions until after you have everything. So if I gave you initial conditions, you just now do, y of 0 and y prime of 0 and stuff like that. So now we're going to look at a case where we have repeated roots and or not even repeated roots. The idea is that your complementary solution and your particular solution, they share the same numbers. So it doesn't have to be repeated roots. It's just that there's a multiplicity, or not multiplicity, there's just a similar behavior, right? So it's more about dependence. So linear dependence of YP. Okay, so here's an example. We're not going to solve the entire problem. We're just going to figure out what is the particular solution. So that's a very important thing is sometimes we don't even want you to solve this. And I've seen people not read the directions and try to solve problems they're not supposed to solve. You're just finding a particular solution, okay? You're just setting it up. You're not even solving the entire thing. So be very aware of that. Sometimes you don't have to go through the entire process. So For this one, we're just going to say determine yp for y double prime minus 5y prime plus 4y equal to 8e to the t. Now, no matter what problem you're doing, you almost always have to find, you will have to find the complementary solution because in order for you to get the correct particular solution, you have to know what the complementary solution is doing. So step one is still going to be formula. Like no matter what the context is, let's just always write this down. It motivates us and tells us, okay, there's two parts to this problem, right? Step two, find YC. So r squared minus 5r plus 4 equals 0. Well, can I factor this? I believe I can, right? Let's see. Minus plus means a minus minus for my roots. 4 times 1 gives me 4. And then negative 4 plus negative 1 is a negative 5. So that works, right? Again, quadratic formula, best friend if you can't do that. So those are my roots. So YC is equal to C1e to the 4t plus C2e to the t. Step 3, determine YP and check YC for any duplicate, right? So we have 8e to the t, right? Notice that we have 8e to the t, but we also have e to the t right here. So we're sharing our complementary solution is part of our particular solution. So the problem that you're going to have is if you don't recognize that when you pick your particular solution, you're going to run into a scenario where you can't solve it. You're not going to have enough information. And just to show you this, right? Yp equal to 8, sorry, a e to the t. If you were to take the derivatives, just so you can see what happens, thankfully these derivatives are very easy. Then if you plug it into the differential equations, a e to the t minus 5a e to the t plus 4a e to the t equals 8e to the t. If I combine all of these together, I get, let's see, that is 5. These all cancel out. And I get 0 equals 8e to the t. If you know anything about the exponential, it can never be 0. But if you didn't remember that, you would do the ln of both sides. Uh-oh, ln of 0, undefined, no good. So this doesn't work. You can't do a e to the t. It's not enough information. There's a dependency. So how do we deal with that? So a to t does not work due to linear dependence. So we just use basically what we've already talked about before. We just add a t to it. So to make independent, we use yp equal to a t e to the t. And that's the answer. You just add a t and you just keep doing that. And the thing is, what if you had two of them that were e to the t? Then you would do t squared. So you just keep adding more and more until you basically uh, get enough information so that you don't run into that issue. But that's all you gotta do. You just add a t. And it's the same thing for cosine and sine. If you have cosine of 3t and then you have cosine of 3t in your complementary solution, you just slap a t on it and you're good to go, right? So let's summarize all of that in words. So for repeated solutions between yc and yp, yp will be yp equal to a t to the n minus 1 e to the t for n uh, functions. that are the same. So if there's two of them, you do t, right? So let's practice an example, just seeing this in action where it's more than one. So example, find yp if y double prime, sorry, not if, for y double prime minus 2y prime plus y equals e to the t. Step one, formula. Step two, find yc. So r squared minus 2r plus 1 equals 0. This is a very common one. So r minus 1, r minus 1. So r is equal to 1, which means y is equal to c1. And we get e to the t plus c2 e to the t. Right? Well, t e to the t. There we go. Now, because there's an e to the t and then there's another e to the t, right? Your t e to the t is not enough to cover all of it, so you actually have to go one step higher, right? So again, the way I thought about it was you just basically say there's one here, there's one here. So there's three of them, right? Three e to the t's, and so you just match it up. So 3 minus 1 is 2. So then step 3 is pick yp. So then yp is equal to at squared e to the t. Another way of thinking about it is if you have like the largest degree in your complementary solution, like if you had like a t squared, always go one higher. Okay. You can always go one higher, and that usually works. I've never seen it not work, but you never know. So that's always a good strategy as well. So, always go 1 degree higher in yp for e to the x. And that usually will be enough to not run into any issues. And again, it's the same thing for sine and cosine. You just put a t in front of sine and cosine. You have to put it in front of both of them too, which just makes it more annoying. So let's practice this idea of just picking particular solutions, not even solving. So here's an example that they may ask you. They'll ask you on the homework for sure. Find an acceptable yp for y double prime minus y prime plus y equal to t squared plus 3e to the 3t plus cosine of 2t. Okay. So the nice thing is you don't have to solve the entire thing. You just got to find acceptable yp. So step one, formula. So y is equal to yc plus yp. You do have to solve for yc because otherwise you can't verify if it needs an extra term to not be independent, to be independent. We've already solved this one before. R squared minus r plus 1 equals 0. So if you were to solve for this is an earlier example. It was 1/2 plus square root 3 over 2i. So then the complementary solution is e to the 1/2 t negative. Was it negative or positive? Let me go back. I think I might have put negative. That went too far. Sorry, I just want to make sure I have the right thing because I remember putting negative earlier. Oh well, I'll fix it later. Uh, and then C1 cosine square root 3 over 2t plus C2 sine square root 3 over 2t. So What I'm looking for is there any matchup? No? Okay, we're good. All right, step two, pick YP. So here's something important. For polynomials, if you're missing a term, you have to include everything. So for the polynomial t squared, yp is going to be equal to at squared plus bt plus c. You have to include everything, even if you're missing something. If you don't, you'll be missing potential information. Plus d e to the 3t plus, and then e comes afterwards, so we'll do it down here. Cosine 2t plus f sine 2t. And for cosine, you got to have both of them. Again, if they both had cosine 2t, you would put, sine 2t, and then you put a t in front of them. So that's one of those things where you kind of have to, you'll see it eventually. So that's how you determine a particular solution if necessary. From there, you kind of have the basic structure of doing every single problem. And the summary of like basically what is the best YP for each scenario can kind of be summarized in, well, there's many tables that you can use, but this table here is a good starting point whenever you're doing these problems. And so it would look something like this. Now, this is grabbed from Paul's online notes, I believe. So if you're doing AE to the beta t, then it's just AE to the beta t, and then cosine and sine are the same. A plus B sine, it's the same thing. So, and then the nth degree polynomial, you just do all of it, right? So that's all they're saying. And yeah, that's non-homogeneous differential equations. So if you're wondering, what should I practice? Practice the easier ones. The exam's not going to be the very difficult ones. And definitely practice finding the particular solution for different scenarios, because that's always important. That's a very easy question that they could ask you on the exam, because these problems are very time consuming, right? So if they're constrained by time, then they'll probably just ask you like set them up, right? So setting them up is just as important as solving them.